Our planet Earth is a fascinating and complex system, home to a myriad of natural wonders. One such wonder, invisible to the naked eye, yet crucial for life as we know it. This protective shield surrounds our planet, deflecting harmful radiation from the sun and keeping our atmosphere from being swept away by the solar wind. Earth's electromagnetic field. But have you ever stopped to wonder what is the source of this invisible force field? The traditional explanation for Earth's magnetic field lies deep within our planet, in the swirling molten iron of Earth's outer core. This iron, heated to extreme temperatures, flows in convection currents, creating electric currents that generate a magnetic field. This process, known as the Geo-Dynamo theory, has been the prevailing explanation for decades. However, the extreme temperatures within Earth's core pose a challenge to this theory, as materials tend to lose their magnetic properties at such high temperatures. Deep beneath our feet, hidden beneath layers of rock and metal, lies the heart of our planet, the Earth's core. The intense heat within the core, a remnant of Earth's formation and fueled by radioactive decay, drives the movement of molten iron, which, somehow generating electrical current, creates the planet's shield, our magnetic field. However, calculations suggest that the heat from radioactive decay might not be enough to sustain the vigorous convection currents required to power the Geo-Dynamo over billions of years. The heat that drives the Geo-Dynamo is thought to originate from two primary sources: the residual heat from Earth's formation and the ongoing radioactive decay of elements within Earth's interior. While these sources provide a significant amount of heat, careful calculations and models suggest that they might fall short of the energy required to sustain the Geo-Dynamo over geological timescales. This discrepancy between the estimated heat input and the observed heat output is what scientists refer to as the missing heat problem. Some scientists have proposed that processes such as the crystallization of the inner core or the movement of lighter elements within the core could release additional heat, helping to bridge the energy gap. The Geo-Dynamo theory, as an explanation of Earth's magnetic field, seems to provide a non-satisfactory answer, yielding only inconclusive and long-standing scientific mystery. However, the missing heat problem is just one piece of a larger puzzle that scientists are grappling with, a puzzle that has come to be known as the dynamo dilemma. In addition to the missing heat problem, scientists are also trying to understand how the Geo-Dynamo started in the first place, and why Earth's magnetic field has reversed its polarity multiple times throughout our planet's history. The dynamo dilemma has fueled a new wave of research and exploration, with scientists developing increasingly sophisticated models of Earth's interior. For centuries, we've gazed upon the sun as the source of light and warmth, the celestial engine that drives life on our planet. Yet beyond its radiant glow lies a force, invisible but immense, that extends far beyond the sun's visible surface, the sun's magnetic field. Earth, nestled within this vast magnetic domain, is constantly bathed in the sun's magnetic influence. Deep beneath Earth's surface, a molten sea of iron and nickel churns and flows within the convecting outer core of the mantle, facilitated by Earth's orbit and rotation, as it cuts its way through the magnetic field lines of the sun, which directly interacts with vortices of liquid nickel and iron, induced by the Coriolis effect, acting as Earth's conductive surfaces. And it's this conductive property of the vortices, in the presence of the sun's magnetic field, that induces an electrical current. This electrical current precipitates two things. Number one, encounters electrical resistance, producing heat, ensuring a sufficiently low viscosity, facilitating the convection. And number two, the electric current produced in the nickel-iron vortices generates its own magnetic field that surrounds and protects our planet, shielding us from the sun's emissions. One such emission, the magnetic field of the Sun, revolves around the solar system approximately once every 27 days. And due to the greater angular velocity of the Sun's magnetic field, it overtakes the Earth 12 times a year. Additionally, the counterclockwise rotation of the Sun and Earth necessitates the side of Earth facing the Sun be rotating in opposite direction, producing even greater magnetic saturation of Earth's interior vortices by the primary magnetic field of the Sun. To comprehend the intricate energy transfer between the Sun and Earth, let's envision a stellar-scale electrical transformer. In our stellar-scale transformer model, the Sun acts as the primary coil, while Earth's molten outer core, a swirling mass of electrically conductive columns of nickel and iron, acts as the secondary coil. So as Earth orbits and rotates within the Sun's magnetic field, the changing magnetic flux induces electrical current within the conductive whirlpools of iron-nickel magma within the interior of our planet, producing the secondary magnetic field that we enjoy every day. This new perspective on Earth's magnetic field challenges us to see our planet not as an isolated entity, but as an integral part of the larger process, starting by recognizing the Sun as the primary coil of the transformer dynamic. The Sun's powerful magnetic field functions as the primary electromagnetic field generator of the solar system. And any object within it, of sufficient area and conductivity, must participate, including Earth's molten interior. Fulfilling the secondary functionality of the transformer dynamic, understanding our complex and inherently interconnected solar system, is essential for the understanding of the larger universe. Section 2. Heat of electrical resistance. We often think of electricity as something that flows effortlessly through wires, powering our homes and devices. However, in reality, even the best conductors resist the flow of electricity to some degree. This electrical resistance, while often negligible in our everyday lives, plays a crucial role in the planet's interior, where it becomes the key to understanding the Earth's internal furnace. As conductive surfaces of Earth's interior interact with the magnetic field of the Sun, an electrical current is induced, and encountering electrical resistance. This electrical resistance, a product of the iron's atomic structure and the sheer amount of current flowing, transforms electrical energy into heat. Imagine the glow of heat generated in a light bulb filament. This heat, a byproduct of the Earth's mantle interacting with the Sun's magnetic field, is a bold and new way to understand the existence of Earth's electromagnetic field. It's a self-sustaining system where the Sun's energy, transformed into electrical currents, is further transformed into heat, maintaining the convection necessary for the process to continue to occur. The heat generated by this electrical resistance isn't just a curious side effect, it's a vital component of this new understanding of Earth's magnetic field. It solves the mystery of the missing heat, providing a sustainable and continuous source of energy that keeps the Earth's interior molten and convecting. For decades, the traditional Geo-Dynamo theory has been the prevailing explanation for Earth's magnetic field, but the dynamo theory struggles to fully account for the measured and observed lack of heat. The Sun's magnetic influence paints a new and more complete picture. And if a Geo-Dynamo could exist, this new understanding can complement and expand on it by solving the dynamo dilemma and associated concepts. However, it is the primary premise of this video to communicate the obsolescence of the Geo-Dynamo concept and the need for an updated model, in which this theory of stellar geo-transformer stimulated emissions of Earth's electromagnetic field describes in great detail. It suggests Earth's magnetic field results from a dynamic interplay between our planet and the Sun. It's a theory that suggests the Sun functions as the source of energy that facilitates the entire solar system, not just the Earth. This perspective has profound implications for our understanding of other planets and celestial bodies. It suggests the magnetic fields of planets are influenced by the magnetic fields of their host stars. It opens up new avenues of research, encouraging us to consider the broader cosmic context. we begin to see the universe as a web of interconnected systems, each influencing and being influenced by the others. It's a reminder that even in the vastness of space, we are connected. Aurora, the evidence of a stellar connection. Have you ever looked up and seen the ethereal glow of the aurora borealis, the northern lights, shimmering across the night sky? These sparkling curtains of light, painted in hues of green, blue and red, are more than just a visual spectacle. They're a critical, if not dangerous, interaction from the sun. The aurora occur when charged particles from the sun collide with atoms in Earth's upper atmosphere. These collisions excite the atoms, causing them to emit light, creating dazzling displays of color. The aurora's intensity is influenced by the sun's magnetic activity. During solar flares and coronal mass ejections, the sun releases bursts of charged particles. These particles interact with Earth's magnetic field, producing and intensifying the aurora, which continue to be a visual reminder of the sun's influence on our planet. Earth, with its dynamic magnetic field and auroral displays, is not alone in the dynamic interplay of energy transfer. Throughout our solar system and beyond, planets and moons exhibit a diverse range of magnetic behaviors, a testament to the interaction between celestial bodies and their magnetic fields. Our neighboring planet Mars once possessed a global magnetic field, much like Earth's, but over billions of years it has weakened significantly, leaving behind only patches of magnetism scattered across its surface. Scientists believe that this weakening was caused by the cooling of Mars's core, which diminished the convection currents required to sustain an electromagnetic field. But now we know it is because the heat created in planetary bodies by 4, possibly 5 separate mechanisms. Number 1, primordial heat left over from the creation of the planetary body. Number 2, a sufficient density of fissile material, which are brought together by the planetary gravitational field and achieves densities required to enable the fission process producing heat. Number 3, friction of material moving past one another inducing heat. And number 4, being the most likely to induce the greatest amount of heat, the electromagnetic inductive heating of conductive planetary interiors of sufficient area as a result of orbital motion within the magnetic field of the Sun. And number 5. While this theory of stellar, geo, transformer, stimulated emissions or SGTSE aims to replace the Geo-Dynamo concept, it may also play a vital role in starting a Geo-Dynamo, facilitating heat, if a Geo-Dynamo was present. And so it can be understood that the interior of Mars has insufficient internal densities of fissionable material, producing an insufficient amount of heat to sustain the convection required to enable induction of the conductive liquid metals within the interior of Mars, preventing the propagation of a secondary magnetic field, induced by the primary field of the Sun, leading to the loss of its magnetic field and subsequently its atmosphere as well. Jupiter, the giant of our solar system, boasts the most powerful magnetic field among all the planets because it contains a massive metallic hydrogen core, which is how its magnetic field is so large. It extends millions of kilometers into space, forming a vast magnetosphere that dwarfs the planet itself. Jupiter's magnetic field was originally thought to be generated by the rapid rotation of a metallic hydrogen core, a peculiar state of matter found only under extreme pressures. But we now know it's the surface area of the large spinning metallic interior of Jupiter that produces such a large secondary magnetic field. Even moons can possess magnetic fields. Ganymede, the largest moon of Jupiter, emits a magnetic field. Due to its proximity to Jupiter, Ganymede generates a trinary magnetic field, which is induced by the secondary magnetic field of Jupiter. That was created by the primary magnetic field of the Sun. These diverse examples of stellar magnetism highlight the complexity and variability of magnetic fields in the solar system and suggests that a combination of internal processes and external influences, such as interactions from host stars, could influence and shape their behavior. Earth's magnetic field, generated and influenced by the Sun, reveals our planet as part of a vast cosmic web. This web connects stars and planets in a delicate dance of energy and magnetism. The Sun's magnetic field extends far beyond its surface, influencing the entire solar system. This influence generates heat, powers magnetic fields, and produces aurora. Our journey into Earth's mantle and the magnetic field it re-emits unravels the mystery and exposes the true source of energy within our planet. It has taken us from the familiar warmth of the sun to the churning depths of our planet's core. We've questioned traditional wisdom, embraced new perspectives, and emerged with a deeper understanding of the forces that shape our world. The true source of Earth's magnetic field, we've discovered, lies not solely within our planet, but in a cosmic partnership with our star. The Sun, our celestial benefactor, provides more than just light and heat. Its vast magnetic field, a force often unseen and underappreciated, reaches out to embrace our planet, inducing electric currents within Earth's molten core. These currents generate the magnetic shield that protects our atmosphere, deflects harmful radiation, and makes life on Earth possible. The missing heat, a puzzle that has long challenged our understanding of Earth's electromagnetic field, finds its explanation as the Sun's magnetic field, which leads to electrical resistance within Earth's interior, generating the heat, keeping the iron mantle molten, and sustaining the convection necessary for this remarkable process to continue occurring. This revelation, this shift from a purely internal to a more interconnected view of Earth's magnetic field, is a testament to the power of scientific inquiry. It's a reminder that the universe is rarely as simple as it first appears, and that the most profound discoveries often lie in the connections we forge between seemingly disparate phenomena. The implications of this new understanding extend far beyond our own planet. If the Sun's magnetic field can have such a profound influence on Earth, what about other planets, other stars, other galaxies? Could it be that the magnetic fields associated with celestial bodies are in fact produced and influenced by an external electromagnetic field and the aurora, those shimmering curtains of light that sparkle across our polar skies? Take on new meaning in this context. They become not just a visual spectacle, but a tangible manifestation of the Sun's magnetic field interacting with our own. The aurora stands as a reminder that we are not isolated observers, but active participants in the cosmos. Our exploration of Earth's magnetic field has opened our eyes to the connections of this universe of magnetism. It's a universe where galaxies influence stars, stars influence planets, and planets influence moons, interacting through vast networks of magnetic fields and shaping the evolution of celestial bodies. As we continue to explore the cosmos, guided by this newfound understanding, we can expect to uncover even more wonders, more intricate connections, and more evidence of the fundamental role that magnetism plays in shaping our solar system. The journey has just begun, and the discoveries that await us promise to revolutionize our understanding of the cosmos and our place within it.